I altered things a little bit. I will still definitely survey a number of problems in here, but we have very, very new results like in the last couple of weeks, and I really want to talk about mostly those. So I'll give a couple new proofs. They're very simple. They're based on classical techniques, but they're nice to see again, and they're new in this setting here. But I'll still highlight a number of the sort of famous results in the area. Well, okay, so the ones that are mine are not the famous ones, but there are some famous ones. And I'll end with some open problems. There's a lot of open problems here still to work on. This is based on, my work at least, is based on two papers, one with Donnie Gebner and another with my new PhD student, Anna Pap. There's Anna with the cool hair. There's Donnie with, well, less hair, but... sorry, Donnie. Donnie's a good friend of a few of us here. Donnie's a new father very recently, so yeah, anyhow. Okay, so I want to start off where I like to start off all my talks here with a couple of quick definitions and then a nice theorem or two. So just so we're on the same page here, if you're working with a graph G, we call it F-free if it doesn't contain a subgraph isomorphic to F. So you fix F, G is F-free if it doesn't contain the subgraph F. It's just a shorthand way of saying this. I always insist that the F in the F-freeness be called F. F for free, F for forbidden. So I'll keep that convention throughout the talk. So if you get lost, F is the thing you don't have. Then the typical Turán question is, how many edges can you have on a graph and still not have an F? And say the number of vertices is n. Usually we think of n as sort of tending to infinity, but you can think about it for fixed n as well. Just the starting point, first example is, say, how many edges can you have and not have a triangle, right? Something like n squared over 4. That's Mantel's theorem, okay? And I'll just call these the first sort of two theorems. This theory here, the first is Turán's theorem here. This is sort of like a weak version of it, but it gives an upper bound when you forbid a clique. So you have no clique on k vertices, no complete graph on k vertices. And this gives sort of a proportion. You know, you can have up to, in principle, around n squared over 2 and choose 2 edges on a graph on n vertices. And this is sort of a proportion here. Sometimes we call it a density, that coefficient out front there. Depends on k. And then there's this far-reaching generalization by Erdős-Szimanovics. It's two papers, actually, that says if you forbid any old graph F, what's important is the chromatic number of that graph F. If we call it K, you'll notice we get the same upper bound as an above modulo some error term, some little o of n squared there. I put equality there. In the other one, you basically have equality as well. Because of what's called the Turán graph, which I'm going to draw. I know it's familiar probably for everyone, but we'll see it a few more times here. So the Turán graph we'll denote it T sub, I'll go with K minus 1. N is a complete K minus 1 partite graph that's as balanced as possible. So you have K minus 1 classes and they're as close in size as possible. So it looks like this. Maybe for k equals 6, so we have 5 classes here. We have all edges between these blobs. Okay. I'll put them all, just because why not? I think that's it, right? There's a star in the middle, something like this, right? And these class sizes are of size n over 5 here, approximately. I say as close in size as possible. If if 5 doesn't divide n, they're 1 bigger, 1 smaller, and so on and so forth. But what's important about this graph? It certainly doesn't contain a K6, a complete graph on 6 vertices, e.g. pigeonhole argument. It also doesn't contain any graph that's 6 chromatic that requires 6 colors to color. Because if you could embed it in there, you'd have a 5 coloring. Okay? And the number of edges in that is precisely what's given there. Well, not precisely, again, modulo divisibility, but it's more or less that. And then same with below, except for the error term there. And I want to say a word about it because it'll come up again. The error term here is important. When k equals 2, so when a forbidden graph is bipartite, right, it's 2 colorable, you'll notice the leading term vanishes. You have 1 minus 1, so the n squared term becomes 0. And so you just have little o of n squared. And we usually we call this situation the degenerate case. The theorem's degenerate then. And we only have an upper bound of little o of n squared in general for bipartite graphs. I find the term degenerate sort of amusing for that category because like that's where all the neat stuff is actually going on in some sense. The theorem is degenerate there. There's a lot of theories still to be done there. There's a lot of open problems for specific bipartite graphs. We don't know their extremal numbers. That won't really be the direction today, though. Okay. So I want to generalize this question, make a direct generalization of it. And instead of counting the number of edges that we can have, I want to count the number of copies of some other graph that we can have. Okay, so fix two graphs, f and h. F is going to be our forbidden graph, and h is going to be the graph we're going to count. Okay, so what's the maximum number of copies of h we can have and still not have a copy of f? So sort of maybe the first question you might ask is, how many triangles can you have in a graph with no f and say f is 6 chromatic? Well, this would be a good starting place, right? This doesn't have the forbidden graph f, if it's 6 chromatic or if it's a K6, but it has a fair amount of triangles, right? You can pick one vertex from 3 different classes, you're going to get a triangle that way, so that's a reasonable place to start, okay? That this is a direct generalization of the Turán question is clear. H being a single edge, 8 is a graph, right? And so this just spits out the question on the previous page when I want to count edges, my graph being just a single edge. Okay. And this topic was initiated, oh, I didn't say that yet. I'll get there next. A famous example that was sort of introduced before this was thought of as a general question was the question where H is a pentagon, so we want to have lots of C5s in a graph and not have a triangle. I'll return to this, I'll tell the results here, but let me draw a picture because this one's very nice here. So lots of C5s, no, I'll prefer K3s. Okay. Actually, maybe I'll ask. So for someone that doesn't know, I mean, there's no way I'm going to know whether you know or not, but what do you think is a good construction here for not having a triangle, or if you even forget that, just having a lot of C5s? Any idea?
Peterson graphs.
What's that?
Peterson graph.
Peterson graph. So, okay, Peterson graph, you're not going to have K3s, you're going to have a few C5s, but I want something general. So n tending to be really large, right? That would work for like n equals 10. That would give you a starting point. What if n is 10? Think about this picture here maybe a little bit. Yeah, take a blow up of a C5, right? So certainly you're going to have a lot of C5s. So it nominally looks like that one, but it's missing things in between there. There's no triangle. That's pretty easy to check. The pair here is bipartite, and if you pick 2 from one, you don't get a triangle either. And this has n over 5 to the 5th. Again, it's up to divisibility, but that's how many pentagons are in that guy. And that ends up being the answer there, although it took quite a while to get there. We'll return to that one. I just wanted to mention sort of 2 concrete examples. Or one. Okay. Yeah, okay, so a bit of notation, and maybe I'll scribble these on the board too, because these will come up a few times. It's good to remember them here. So, NGH, this is the number copies of H in G. So you have some host graph G, and you're actually enumerating the number of copies of H in it. That's what this notation is. Yeah, thanks, Andres. That's a typo. So we'll go, is that a typo? I forget which one we should use. When it comes up, I'll confirm which one it is, but yeah, this is actually a good argument for a different piece of notation. Maybe I'll explain what I mean by that. This one here, this is in the right order. So this one is this extremal number. Remember, well, actually we didn't introduce the other notation here, but this guy, EX, N, H, F. F is the forbidden graph. I promised you that will always be. So this says no F, and this one is the number of H's. And this just records what's the maximum value of this, what's the maximum quantity over all n vertex graphs that don't have an F. What's the maximum number of H's we can have? So if we don't know it concretely, it's a theoretical quantity that does exist. Okay. Oops. And then finally, as a general topic here, studying this function here, trying to understand it, especially as n grows. This was initiated by Alon and Shikhelman. A number of questions pertaining to this function were already asked and discussed and answered before they introduced this piece of notation. Let me mention one other piece of notation for it because it comes up in other places, but I'm not going to use it because I want to follow theirs. But you can make a good argument that this other piece of notation is better. And you put a little subscript h here. Right? You can see what maybe some of the advantages this has. The disadvantage is that often h here is denoted with itself a subscript. I really dislike nested subscripts. That's just a personal thing. So anyway, but if you prefer this, you can think of that in your head there. Okay, so let's get to some actual results now. And so the first theorem here is essentially a Turán's theorem for this subgraph count question here. Okay, so fix two integers n and r, let r be less than n, r be less than k. The maximum number of krs that you can have in a graph with no kk, so maximum number of r cliques in a graph with no k clique. You can see k ought to be bigger than r, otherwise the answer is 0, of course. It's given by the number of copies of kr in the Turán graph. Okay, so this is wrong then, right? According to that. So let's change it around here. I'll be consistent with the slides. All right. Maybe that makes more sense anyway. It's given by that, and then I've just estimated there with this error term that's actually a little bit more aggressive than the truth. It's just the number of copies of kr in the Turán graph. If you look in this thing here, say r is 3, you can easily estimate the number of triangles. What is it? It's approximately number of classes choose r, which is one vertex from each class. And then in each class you had n over k minus 1 choices for that single vertex raised to the r. So it's that. If you want a concrete upper bound, you can just round up there. You can determine the error term there. It's not, it can't be, it's n to the r minus 1 or something like that, or even smaller. It's really just a constant error there. Okay? So it's an exact result. This actually says that the Turán graph is the unique graph that achieves this as well. So it maximizes all krs. And that completely captures Turán's theorem, because Turán's theorem is just this, what I'll call Zkov's theorem for r equals 2. Right? An edge is a clique of size 2. How do you prove this? This is really cool. So Zkov 1949, I mean, this is another proof of Turán's theorem. That's what he proved in 49, was another proof of Turán's theorem. But it turns out he proved more. He actually proved this clique versus clique result here. That's in the paper. So his symmetrization works for that. It actually proves more things. This technique's been used a bunch of times. And this theorem in this form has been rediscovered. You can see by Erdős. That's an Erdős's proof of Turán's theorem, which was an induction on K. It actually gives a stronger result here as well. This proof, this is an excellent exercise for like your PhD students on like a comprehensive exam. It's not that difficult, but it asks, do you know how to symmetrize? Because you usually teach the symmetrization to max edges, but you can max triangles or K4s or something like that. In fact, to my knowledge, just about every proof of Turán's theorem, and there's a dozen of them, can be adapted to work in this setting here. So it's a good way to test how well one understands the question. But anyway, so it's really kind of neat there. All right. So now I'm going to give this name. I'm going to try to name a bunch of my theorems so we can keep track of them. This is going to be the fundamental theorem, which is an Erdős-Stone type result here. This says that if I want to count krs and I forbid f now instead of just the k clique, and f has chromatic number k, then the upper and lower bounds are essentially the same as what was given by Zkov's theorem. Now that error term is a true little o n to the r. You can get something like n to the r minus epsilon in your error term there, in principle. But the point is the Turán graph still works as an a lower bound, right? This doesn't. If this has k classes, k minus 1 classes, it doesn't contain f. That's k chromatic, and the number of copies of kr is approximately what's given in the first term there, that n to the r term there. Okay. As I pointed out here, when h, the graph you're counting, is k2, it's exactly Erdős-Stone-Shimonovich theorem. And the proof of this follows the proof of the Erdős-Stone-Shimonovich theorem by the regularity lemma. That's a classic exercise as well. You can just follow that proof. This is another great exercise, by the way. So it doesn't require much tweaking, but it's a good way to just have some exercises. There aren't a lot of good exercises using regularity, right?
Is there a proof without using regularity?
Yeah, I'm gonna. Well, okay, I'm gonna tell one or not tell one. I'm gonna mention it. You mean of Erdős-Stone-Shimonovich without regularity? Yeah, certainly.
There's one.
Yeah. So this one, yeah. I'm going to tell later a supersaturation result, which implies it, that we don't use regularity in part of it. Maybe it can be adapted. I haven't actually tried to take the original Erdős-Stone proof and work it here. It may work as well. I don't know. It's a good question. It'd be nice to actually see if that's possible. So, and then there's this, I'm going to call it Degenerate Theorem here, which kind of tells us what the degenerate case is. For this counting function. Notice the discrepancy between these two. Up here in the fundamental, it's not as general as it can be. I'm only counting kr, so I'm not counting some general h. I'll get to that in a little bit, why that's kind of an issue. But this degenerate theorem tells us at least when the order of magnitude of this function, h versus f, is not n to the number of vertices of h. This n to the number of vertices of h is, of course, as order of magnitude, it's the clear upper bound. you can't have more than n to the size of h copies of h, right? Each vertex, you have that many choices. But what I want to know is when does it drop below that sort of max range there? And it happens in this very simple condition here, just simply when f is a subgraph of the blowup of h. What's the blowup of h? Say h is just like a triangle or something. The blowup of h is, all I do is replace each vertex of this thing here with t copies of itself, right? So I have these, and then I just connect everything between the classes here. I mean, in this specific instance, the blowup of this happened to be a Turán graph, but I don't want to think of it that way. It's just a specific copy here. Okay. So if f is containing the blowup of h, then you get this little low condition here. I think this is actually equivalent to whether or not h contains a clique with the chromatic, whose size is the chromatic number of f, right? If it contains a clique of that size, you blow it up, that clique will end up containing f. I think it's an if and only if as well. Maybe it's worth thinking about for a little bit there. But this contains a little more information than what, because up there we certainly get this little low condition for k of r, right? But that's only for k of r. This talks about for general h as well. And this proposition will be important to us later as well. Okay, so now the first sort of new thing here is the stability theorem. So the first thing here was like, how do we even form a stability theorem for the subgraph counting problem, right? So okay, so first of all, this hasn't been published, but there's 3 different sets of authors here, 3 different papers, all have different proofs here. I'm going to tell our proof because, well, I mean, of course I'm going to tell mine. Well, okay, it's maybe not of course. So if the number of KRs in your graph in G doesn't exceed the extremal number, but it's close, right? So it's off by a little of n to the r, then you're not far from being a Turán graph in terms of edge changes. Now one could ask, well, is the number of adding and removing edges the right thing? Maybe we should talk about adding and removing KRs or something like that, and then be few of those or something. To me, it's a little bit convoluted, this notion anyway. What does it mean to change a KR? Changing, adding and removing edges anyway, okay? So this is just like the ordinary stability theorem. If you replace r with 2, it's precisely the ordinary stability theorem. You're close to the extremal number, a little bit below, you're not far from being the extremal graph, which is the Turán graph here. And before I prove it, I want to mention a problem here. This is something that I really want to know the answer to, and I'll try to explain why it's a little bit confusing here. So this is stability, but not in the most general sense here. I'd really like a stability for h and f, right? Now we don't have a theorem answering the question we don't know the extremal number for all h's and f's, so I'll explain why in a moment here. Or even this case here, where you forbid kk and just count some other h. It would be nice to have a stability for that, but I can't get that to work with the theorem we have here. Let me give a rough idea why that is. Well, the first reason is, in general, the Turán graph is not the extremal graph for those things there. But of course, you can still ask for a stability that it can be changed into whatever the hypothetical extremal graph is, even if we don't know it, with relatively few changes. Well, of course, the Turán graph's nice, so it's easier to show you're close to that. But let me give you 2. I'll erase this one here. Maybe 2 little examples here of why this is kind of interesting as a question on its own. If you look at this extremal number, n vertices, and let's take a star. Oh, I have a chalkboard, so I can actually like do this. So that's the graph I want to count. Say it has r vertices here or something like this. So r plus 1 in total. Then I want to forbid, like, let's just say a triangle. Right? So your first suspicion would be, well, it's probably a complete bipartite graph. And it is a complete bipartite graph, but it's not a balanced complete bipartite graph. Let me just, I mean, it's an optimization problem, but let's just look real quick. If you have n over 2 here and n over 2 here, what's the number of copies of this star here? Choose a vertex here, and then choose r vertices here. Right, that's a copy of the star, so you have n over 2, choose r, times 2. You could have done it in the reverse fashion there. But just as an example here, what if I took n over 3 and 2/3 n, 2n over 3, and you write something very similar here. You choose one vertex here and then r from this. There are more of this type, so I'm only going to count those. You do your arithmetic. This one's actually bigger here. It's an optimization in terms of like r. You have to figure out how to balance the classes. But this is not a Turán graph. These are not as close as possible anymore. And you can imagine the situation gets worse. What if I forbid instead of a triangle a K4? then I probably should have 3 classes, and who on earth knows how to balance that? Actually, it's quite possible that you actually still want to drop down to a bipartite. I don't know. And then, just to really make it awful, instead, if I replace this, suppose you put like some complete. Let's make this bigger here. Let's forbid a K12, and then let's count the number of copies of a complete multipartite graph with class sizes 2, 5, 101, or something like that. Just imagine the optimization problem now, right? I mean, so there's a nice paper by J.D. Neer, John Cutler, and Jamie Radcliffe who are trying to figure this stuff out, but it's very detailed, and it kind of escapes these really pretty examples here, as it needs to. But this is what makes making a stability a little bit scary in this situation here, because who knows how many edges that has. And, I mean, we can refer to this hypothetical graph and just say it's close to it, but I don't know how to do that. Okay. All right. So I want to give a proof of this stability theorem here, and like I said, it'll be on the slides here, so I'll try to go through it very slowly. But let's just remember what we're trying to do here. We're going to start with G. Oh, I bet I have a lemma first. Okay, but let's still remind ourselves. So I'm going to have a G that has this many copies of KR, slightly less than the extremal number, and we're just going to want to show that it's close to the Turán graph. And the strategy here that wasn't used in the other papers, I want to use ordinary stability. So I want to show that it has close to as many edges as the Turán graph. Now, at first, it seems like that's got to be true, right? It's got about as many copies of KR as in the Turán graph. Shouldn't it have about as many edges are in the Turán graph? And if we could prove that, we'd be like done immediately. But somehow this is very difficult to prove. Because of the way that KRs are distributed, they don't necessarily have to give as many edges. Now, we'll end up proving that. But we have to take a detour in order to do that. So we need this lemma.
So
Yeah.
in the case of the star,
Yeah, sure.
the solution to that optimization problem is the answer.
Yes, that is the answer. That's known, yeah. So actually, if you go back to Zkov's theorem will tell you that if you have a complete multipartite graph here of any fashion, and a clique here, the extremal graph is complete multipartite itself. It doesn't say that it's balanced, though. So you know it's that, and then from then on, it's just optimization, right? So, And, the first time I thought about this, I was like, oh, it's surely Turán's. That's got to be the best and done. And then, fortunately, someone was more careful than myself. And, So this lemma actually captures a lot of the stability proof. I'm not going to go through the details of it. I won't prove it. But what it says, actually, here roughly, is that if there are lots of copies of your graph H, like the first line there, so we're still KK free, and we have lots of copies of H. Notice it's slightly less general here. Let me jump back for a second. The number of copies of H is bigger than the extremal number forbidding a KK, not an F. In the previous theorem, I'm forbidding an F. Here, I'm only forbidding a KK. It's a slightly different situation. I'm going to have to get my graph KK free, right? If you have no copy of F, you might still have copies of the complete graph on K vertices, even if F has chromatic number K. Right, the chromatic number is not strictly enforced by the clique number, right? We're well aware of that. Then what it says, it has a subgraph. I didn't define alpha. Alpha is just, you can make alpha as small as you want, as long as it's large enough. It contains a subgraph such that every vertex is contained in many copies of H. Okay, what is this N over R? This quantity here says that it's, let's put it right here. Basically as many copies as in the extremal graph. So it gives some kind of degree condition, but not a number of KRs. So every vertex has about as many KRs on it as would be KRs on the vertices of this guy here, approximately. Okay, so this is actually clearly a type of stability result on its own immediately here. But we're going to use this lemma actually to prove the more general thing. This lemma is based on a stability lemma of Sergei-Norien that works for hypergraphs, and it's not too difficult to adapt it to this setting here. It doesn't follow directly, you have to do a little bit different, but it's a relatively basic counting and induction. Okay. All right, so using that, let's prove the theorem here. Okay, so this was what the theorem supposes. The number of KRs is slightly, just above, a bit less than the extremal number for no F, counting the number of KRs. The first thing I'm going to do is actually count the number of KKs. K is bigger than R, right? K is the chromatic number for F, the forbidden graph. So like I said, there could be copies of K. So let's figure out how many of them there are. So immediately we know that the number of copies of KK is at most the extremal number for the number of copies of KK in an F-free graph. Our graph doesn't have an F. right? So the maximum number of KKs it can have is the extremal number there. And then it says this is little o of n to the k. This is Alon's Degenerate Theorem from the beginning there. Okay? But actually this follows from a more general theorem of Erdős that basically says the extremal number for a hypergraph of chromatic number k, for a hypergraph that's k uniform versus something that's whose chromatic number is k, it's little o of n to the k there. Okay? Basically the reason is if you have too many copies of kk, you will have a blow-up of kk, but a blow-up of kk contains f because f is k chromatic there. Okay? I'm not proving that. That's just already a theorem of Erdős. Alon and Shikhelman. Okay? So what I want to do, I want to get rid of the copies of kk because I want to apply my lemma to a kk-free graph, not to an f-free graph. Well, that's easy removal lemma, right? The number of copies of kk is little o n to the k. This screams use the removal lemma. The removal lemma says that if you have little o n to the k copies of a graph on k vertices, then you can destroy all of them by removing little o of n squared edges to get a new graph G prime that doesn't contain a kk. So here's where we actually use regularity in this proof. However, this step is redundant if f itself is kk, right? That's one instance. F could be kk. Then the observation is that it's 0. You don't need to use the removal lemma. Okay. So now I have G prime, and I've removed all the copies of kk from it through the removal of little o of n squared edges. How many copies of kr have I destroyed? I don't want to destroy too many copies of kr because I need to say something about them. But fortunately, if I destroy little o n squared edges, I've destroyed at most little o of n to the r copies of kr because it's just r minus 2 more vertices to be added on. So the point is, if you look at the top line there, the number of krs was the extremal number minus little o of n to the r, and I lost another little o of n to the r of them. So what? Nothing changes. So now G prime is kk free, not just f free, but kk free. And the number of copies of kr is basically what it was before. This is what it was, it started out as that, I subtracted another little o, and then this has a clear lower bound of this guy here. So I still have this minus little o there. Why is this a clear lower bound? This is the Turán graph, exactly, and the Turán graph is a lower, it doesn't contain an f. It's obvious, but it took me a moment there to figure it out myself. Okay, so by the previous lemma, now we have exactly what we want. We have the number of krs. That actually is a little more general. It works for h, but we're applying it to just kr. It contains a subgraph G2 primes, where each vertex is in about as many krs as the Turán graph would have had krs. Okay, so now we're getting close to it looks like the Turán graph, but we still don't quite have it. Now we have another lemma here. This is a pretty simple counting lemma here, but it says, it connects this line to this line here. It says that if you have a graph, and every vertex is in about as many copies of kr as the Turán graph, then the actual degrees in that graph are basically the minimum degree in the Turán graph. This is not hard to argue, but it's not one line, actually, surprisingly. Well, it's 2 lines, maybe, but it's not a hard lemma, but somehow it's just not immediate. And it goes sort of kr degree to degree, and what we ultimately want to conclude is number of edges, which of course follows from the minimum degree condition. If we could jump from number of krs directly to number of edges, we could skip everything in between. But somehow that you have to go through this degree route to get that to work. Okay? But what's this last line say? This last line says we can just apply ordinary stability, right? Where G is f-free, it has this many edges in it, now we've concluded. And so ordinary stability says that it's within little o of n squared edges of being the Turán graph. So we just apply stability, and that's the end of the proof. Okay? There's a slightly different way to do this while avoiding stability, while building up some kind of subgraph that's complete multipartite and so on, but I actually really like just applying ordinary stability. Okay, so that's that guy there. Now, after stability, after the characterization theorems, supersaturation is the way to go. So this is totally new here. And there were a couple supersaturation results already proved. There was supersaturation for clique versus clique. So when H and F are both cliques. And there was also a supersaturation result when H is a star and F is a clique. Actually, which is interesting because that's in this scenario where things are a little bit weird. There's still a supersaturation. So what does supersaturation say, if you're not that familiar? So ordinarily, supersaturation says if you have more edges than the extremal number, you definitely get a copy of the forbidden graph. That's the definition of the Turán number. But what's more is that you get lots of copies of the forbidden graph. Right? You get n to the f copies of the forbidden graph. In this general setting, though, it says if you exceed the extremal number by, well, little o n to the h, you can make that constant as small as you want, then you get, sorry, not little o n to the h, some positive constant n to the h, then you get n to the f copies of f. So having lots of copies of edges gives you lots of copies of your forbidden graph, but also giving lots of copies of h, the graph you're counting, beyond the extremal number, gives you lots of copies of the forbidden graph there, okay? The proof of this is totally standard. You just follow Erdős's supersaturation result that he proved many years ago. But I want to go through it because if you haven't seen it before, it's really cute. It does have to be changed slightly for the setting, but it's not very difficult here. Yeah. No, it's not. Yeah, okay. Oh, it's the same as CF, yes. Yeah, same as CF. Somehow I don't like alpha, delta and epsilon in this case here. I don't know why, but you know that you could have just simply epsilon for the first CF and delta for the CF. Yeah, there's no CL in CF. I don't know why. Thank you. Okay. Before I prove this, I'll mention it has one consequence here. Something. Okay, this is embarrassing to call my own result fundamental theorem 2. I just wanted to give like it a name that fit with the other one here. This is something Donnie and I proved. It just came out this year. We proved it a couple years ago. This is a generalization of the Alon, Shikhelman, Erdős-Shimonovich type result here. If you plug in H is a KR, you get exactly their result there. Because here you have KR versus KK, which we know. It's not written anymore there, but it's the exact term they had there with the same exact error term there. This thing's a little bit more general. It's, again, you can prove this using regularity. But you can actually prove this from supersaturation, and the proof of supersaturation doesn't use regularity. So actually, to answer your question, Songil, this would give a proof of this without regularity, but there's still another option to go through the original Erdős-Shimonovich way. I won't give that proof. This is actually pretty standard. Supersaturation can be used to prove Erdős-Shimonovich. You just do what they did to get the corresponding theorem. Okay. So how does this guy go? Okay, I'm proving let me just jump back here, the supersaturation. So remember, the number of copies of H and G is more than the extremal number there, this C n to the H more, and I want to find a bunch of copies of F, so n to the F copies of F. Okay, so how are we going to do this? First, I'm going to put Q equal to this limit here. So as n goes to infinity, the extremal number of numbers of copies of H versus a forbidden graph F, divided by n choose h, which is approximately the maximum number of copies of h you can have. You can throw in like an h factorial in principle because you can have a bunch of the same, but it doesn't change things. So the first question actually should be here is, does this limit even exist? Because for graphs, it does, but it needs to be proved. Same proof works here. It's a very nice double counting argument. It's due to Nemetz, Katona, and Shimonovich, from a pretty old paper that's in Hungarian. But this is a well-known thing in the graph case, and hypergraphs it works as well. And here in this slightly different subgraph counting instance it works. Maybe another good qualifying exam question. I'm always looking for these, so you know. So we'll put Q. This will just make the notation a little bit easier there. So now we can rewrite the initial condition on the number of copies of H in this following form here. We just have a Q plus C and choose H, right? If you just rewrite it in that form, just take the limit there. Okay, so G satisfies that guy instead there. Now I'm going to choose an M that's large enough. Right, now notice this extremal number gets closer and closer and closer to Q times M choose H, or Q times N choose H, right? And that's what it means to be a limit there. So we can choose M large enough so that it's within C over 2 as an additive constant inside there of the thing of M choose H. Okay? So think of M as growing, but maybe it doesn't quite reach up to N, and N's really tending to infinity. Okay, and then we're going to make this assumption for the sake of a contradiction here, that, let me draw a little something here so this is a little clearer. So I've got my n-vertex graph here, and I'm looking at subsets of size m. M is the value that satisfied that condition above there. So I look at sets of size m, and I'm curious about the number copies of H inside of that M set. Okay? So I have lots of M sets. I have N choose M sets, of course. And each of them is more or less dense with copies of H, right? It depends on what my graph looks like. And I want to assume that there are relatively few, so less than C, just some constant. H factorial H is the number of vertices of the graph H. n choose m, so less than that many of the n choose m sets who span a relatively large number of copies of H. Okay? So fewer than this, many of the total n choose m span more than this. More than this is what's important. Copies of H. This quantity, though, is larger than this. That's just by the definition of m there. It's just a reminder. There. Okay? So we're going to try and contradict this, and we're going to do that by counting something in 2 ways. So I'm going to count the following thing in 2 ways. And from here, it's very simple. I'm going to sum up over every set of the vertices of size m, the number of copies of H in that set S. This is a slight abuse of notation. S is not a graph, it's a vertex set, but I think it's evident what I mean here. It's the graph induced on S, the number of copies of H in it there. And I'm going to count this in 2 ways. So with the assumption above, this is bounded above by this quantity here. This is the number of copies that are relatively sparse, the number of vertices spanning more, no, sorry. This is the number of M sets that are denser. How dense they can be? They can have M choose H times H factorial copies of H. That's just like if that M set is complete. You can have that many things there. And then the remaining, it's actually 1 minus this times N choose M, but it's an upper bound, so I just throw the rest out. It's 1 times this bound here, that's the maximum number of copies allowed in the relatively non-dense things. And you just combine these things here, and you get this maximum bound here, Q plus C there, for a lower, an upper bound, for an upper bound in this guy here. And then the lower bound, oops. The lower bound is counted in the following way. This one doesn't have the words to describe it, so let me point it out here, but this is easy as well. How can I count the number of copies of H in S summing up over all S sets? Well, let's just look for copies of H. So that's a copy of H. How many times is it going to be counted in this thing? Well, it'll be counted as many times as there are M sets that I can build up around it. Okay? So number of copies of H, that's the way to build an M set around it. The number of copies of HG is greater than or equal to, from that line above there, Q plus C, N choose H. So I have this identity here, and this is my favorite part. Like this and this, remember Vandermon's identity? That's Vandermon's, right? Or no, that's like a generalized chairperson. Whatever his name it is, it's this, which is that. But now we have strict inequality between these 2 equal things. Here it's a contradiction, right? And so now we're basically done with the proof, because the line above that, assume for sake of contradiction, doesn't hold, so it means that they're more than C over 2 H factorial N choose M M sets. So combining these with contradiction, so this many M sets that each contain a copy of F, and each copy of F is counted at most this many times among these things here. So if you divide this guy by this guy here, what do you get left in terms of order of n? You have n to the f. Right, here's n to the m divided by n to the m minus f. You have n to the f. And the constant you can work out, it's a bunch of those things depending on h factorial and so on. But we got the number of copies of f that we wanted. And then we got some constant times n to the f copies of f. Right? So that is the end of that proof. And okay, I have enough time to survey some of the prior results. So maybe this talk is like backwards. I started with the new stuff and go to the old stuff. But so let me highlight a few more very interesting questions here. There's one more proof, but I think I'm going to skip it here so I can talk about these things here. So I mentioned earlier on maximizing C5s in a triangle-free graph. And it was a very nice construction. The blow-up of the pentagon was n over 5 to the 5th. And the upper bound here is given by these 2 groups here, working simultaneously, both using flag algebras. To me, the coolest was flag algebras. There's a bunch of cool ones. I really think this one's awesome. It gives basically the exact result here. There's divisibility issues, of course, but I always assume n is like I want. So, and this was an old conjecture of Erdos, and there was a result of Jury that it was 1.03 as an upper bound, n over 5 to the 5th, and this was improved as well, I think, in some unpublished paper by Furedi. Maybe there was even an additional improvement. But this is sort of, in a lot of ways, maybe the most famous subgraph counting problem. It still hasn't been proved without flags. I believe this is still the case. So those of you that don't like flags, you can try that. It'd be interesting to see an elementary proof of it nonetheless, but I think that's great. If you swap the roles of K3 and C5 and now maximize the number of triangles and have no pentagon, maybe this is less natural. You have these upper and lower bounds here. This is an open problem still. The order is n to the 3 halves. It's dramatically different than the order of magnitude in the previous case. And actually, if you think about the degenerate theorem for a minute, it makes sense, right? In the theorem above, if you blow up a C5, you don't get a K3. I mean, that's the whole lower bound relies on that fact. So the top one is not in the degenerate case. It's not little o of n to the 5th. But the bottom one is, if you blow up a triangle, you do get C5s in it, right? You get 5 cycles. So this one, that would give an upper bound of literal n to the 5th. We can do quite a bit better, obviously, by this result here. But order of magnitudes n to the 3 halves, upper and lower bounds given by Bolovash and Yuri were these. They've been improved. Abi, am I right? Is it 0.232? Is that what you don't remember? So yeah. So. But it's not 1 over 3 root 3. So this is definitely another place, something I'd like to see answered entirely. Yeah, that's a possibility. Yeah, we were actually already talking about it this afternoon a little bit. So, yeah, there we go. Here's another 2. These are sort of samples from Alon and Shikhelman paper that are pretty nice. These are answered questions essentially. So if you want to have a lot of triangles in a KST-free graph, you get this nice n to the 3 minus 3 over s, which is reminiscent of the maximum number of edges in a KST-free graph, which is big O of n to the 2 minus 1 over s. This theorem below is just it's a generalization of that. It doesn't tell all the information because this upper bound still holds outside of this region here. But it's just sort of a complete nice theorem there with order of magnitude. As long as S, T, and R satisfy the appropriate conditions here, you can get exactly the order in this one. And then Alon and Shikhelman also determined this extremal number when you count the copies of one tree and forbid some other tree. They do find the order of magnitude, but you can't like write out what quantity it is. It has to do with the number of ways to embed T1 into a blow-up of T2. Unfortunately, this is one of these theorems where like it's a great theorem and it's true, but writing it down is ugly and there's just no escaping it. That's like the universe's fault in this case, I think, for now at least. So, okay, so this was the direction I was gonna go and prove. When do we end? Do you go 50 minutes or the full hour? Oh, I don't even need that much. I mean, I meant like, yeah, so, yeah, so. I'll try to wrap it up. Maybe I will give that short proof because it's kind of cute here. So this doesn't follow from the previous result. You know, this is a nice asymptotic result here, right? Count triangles in a K2T free graph here. You get this 1/6 T minus 1 to the 3 halves and the 3 halves. You have an upper and lower bound there. The lower bound is really nice because the lower bound is the same exact graph that maximizes the number of edges in a K2T free graph. You have this Tura construction. It's like a projected plane. And if you go and count the triangles in it, you get that quantity there, and then you can actually put an upper bound as well. And what's really nice about that Tura graph is that it maximizes other stuff too. So with Donnie, we proved it maximizes the number of cycles and it maximizes the number of paths there, and you get asymptotic results here. There are some conditions on K. I think one of these is, which is the amusing one? I think this one here, right? K ought to be at least 4 because, well, I mean, you can have C4s and no K2T, but like if T is 2 and C is 4, then you're counting the number of C4s in a K22 free graph. But K22 is a C4, right? So actually we have that case filled in as well, but then T has to be lower. So it's not written out there. Okay? But both these are achieved by the Tura graph. You go in and count the number of copies of those things, you get those. And let me show you how the upper bound is proved in these cases too, at least for one of them, because it's easy and interesting. Well, I mean, it's drawn on the slide here, so I guess I don't have to write anything on the board. Okay, so we'll prove it in the case where we're counting cycles, and let's say K is odd. The even case isn't too different, but the odd case is just easier to show here. So we start with G. Its n vertex has no K2T, and we want to count the number of CKs in it. Okay. So what I'm going to do is I'm going to fix a tuple of vertices. So K plus 1 over 2 vertices. So that's why we wanted K to be odd. So K plus 1 is even, so that we don't have to round down or anything like that. So I take this tuple, x1, x2, up to xk minus 3 over 2, and then 2 more vertices, yz. I give them a special name because I require that they form an edge. The other vertices in the tuple don't have to form an edge. They don't have to have any relationship with each other. Okay? The number of ways to pick this tuple is at most this guy here. I have to pick the edge yz. That can be picked in the number of edges ways times 2, because the edge could be yz or zy is the same thing there. And then the remaining vertices x1 up to xk minus 3 over 2, each of those can be chosen in most n ways. Obviously not, after choosing the first you have less than n ways for the second, but it's an upper bound here. Okay. And then Turán tells us the maximum number of edges in a K2T free graph. So it just gives us an upper bound on this E of G. Right? So it just tells us this guy here. Turán says 1/2 t minus 1 root t minus 1 n to the 3 halves. So that's this term here. The 1/2 and the 2 cancel. So you get this quantity here. There's an upper bound on the number of ways to pick this tuple. So now that I've picked the tuple, what I want to do, I'm going to show this in the next slide, but it's better to. I'm going to arrange the tuple in a circle like this. Here's the edge here. And this is basically half of the vertices of the cycle. Actually, it's a little bit more than half the vertices of the cycle. I want to know how many cycles I can find that fit among these guys here. So I have to find like another vertex to go there, and then another vertex to go there, and then another vertex to go there. And if I finish that, I'm counting the cycle. So I know the number of ways to do that. So number of copies of CK of the following form. You can see the xi's are every other one, and then the yz, the last two there. It's odd, so that's how it works out there. But this is actually pretty simple because between any two vertices identified with a name, x1, x2, there are most t minus 1 choices because every two vertices have at most t minus 1 common neighbors. If they have more, then I have a K2T. So now I'm using the K2T freeness. And so that's the number of choices at each step there. And that says the remaining vertices are chosen in at most that many ways. There's k minus 1 over 2 opportunities to make a choice. You have to double check that, but that works. This will count every cycle, because every cycle can be represented by this tuple and then fill in the remaining edges. The only thing to figure out is how many times did you overcount cycles, right? This will count cycles too many times. But whenever you're overcounting cycles, it's always like the same thing. You've got reflection and rotation for the number of ways it's overcounted. They're all overcounted 2k times. Sorry, just 2k times. So you have to throw that thing in there. You go through that, and we're done. You just simplified, and that's the upper bound that we gave there. For even cycles, you don't have this extra edge, but you have to be a little more careful. And for paths, something very similar works. You don't have to loop back around, so you get one more term in t minus 1. Okay? All right, so let me wrap it up with a couple problems here. There are many more, but here's a few that I really like, in addition to a few of the others I mentioned along the way. So here's, like, for me, the first concrete question in this area to answer, and I don't think this is very, very tough. I've asked this here and there at a few conferences, and everyone sat down and determined, some upper and lower bound, but it still evades a complete, solution. This just says, remember the famous maximize pentagons, forbid a triangle? This says instead of forbidding a triangle, forbid, I like to think just of a K4. It's definitely not as natural. The answer is not going to be a blow up of a C5 probably, so it's not going to be as pretty, but it would be interesting to answer this. This is a good starting point if you want to work on a concrete individual problem. This is a famous problem by Erdős. This was asked a long time ago. Maximize the number of triangles in a graph that does not contain a blow-up of a triangle. So even if, KR222 is, 2 vertices, 2 vertices, 2 vertices, and all edges between them. And this is kind of supersaturation result in itself. How many triangles do you need to start forcing these blow-ups? You know that they happen eventually. This is little o n to the 3, but it'd be better to say something more than this, okay? This has been open for a long time. Actually, even asking things like K122 is interesting, right? That's one of the I forget these graphs, right? So that one's already interesting as well. What about K112? I don't know if that's interesting or not. Well, it's not uninteresting anyway. So
That's known.
That's known, K112. Okay, I'll think about it afterwards. So. And then this one, this is a whole other direction that was thought about a while ago by Pop, Simonovich, and Jury. We saw some graphs that were not maximized by the Turán graph when we're counting, right? The stars, the weird complete multi-party graphs are not maximized by the Turán graph. And a lot of things are definitely maximized by the Turán graph. If we forbid a clique, count another clique, and so on and so forth. But just to give a sort of more general question here, when is the Turán graph the best thing? When can you not add other stuff? We don't have a general answer to this question. It'd be nice to have one. I mean, this is actually, even in the graph case, when h is 2, this is an okay question as well, right? When does the Turán graph maximize the number of edges? It's a direct question you could ask. Yeah. Okay. So thanks for your attention.